Have you ever wondered why bridges don't fall? Thousands of cars, tons of concrete, wind, current, time, and they are standing. We see only the upper part beautiful arches, wires, lanterns, but the most important thing is hidden from our eyes. It's underwater. There, in the darkness and cold, a real battle between man and the elements takes place. Deep at the bottom of rivers and bays, foundations are built that hold giant spans. And today, we will go down there. How can you build underwater? How to pour concrete if there is water around? How to make a support if the bottom is soft like a pillow? Let's figure it out. At first glance, it seems arrived, poured concrete into the water, and it's ready. But it doesn't work. If you just pour concrete into the river, it will be washed by the current. It will turn into muddy porridge and will never freeze as it should. Water washes away the cement milk, and the mixture loses strength. In addition, there is almost always silt, sand, or clay on the bottom. Imagine that you are trying to put a heavy cabinet on an inflatable mattress. Nothing will come of it. The support will simply sink and skew. So you need to get to hard ground. But how to do it underwater? How to organize a workplace at the bottom of the river? Engineers have come up with three brilliant ways, and each of them is a small victory. The first method is called a caisson. Imagine a huge inverted box without a bottom, only the walls and the ceiling. This box is lowered to the bottom of the reservoir, and then powerful compressors begin to pump compressed air inside. The pressure inside becomes higher than the water pressure outside, and the water can't enter. It turns out a dry air bubble in the middle of the river, a real underwater bell. The workers go down to the caisson through the lock chamber, and do you know what they are doing there? They just dig with shovels. Under the walls of the caisson, they take out the soil, and the structure slowly sinks deeper and deeper, centimeter by centimeter, like a huge glass that is pressed into the sand. And so it goes on for weeks, until the caisson reaches a hard rock or dense clay. Then they start pouring concrete inside. It turns out a monolithic support that stands for centuries. In the 19th century, it was a real revolution, but there was also a dark side. The deeper the caisson, the higher the air pressure. The nitrogen in the workers' blood began to bubble like in soda. It caused excruciating pain, paralysis, and even death. It was called a Caisson disease. Today, this method is rarely used. It's too dangerous and for a long time. But it was he who opened the era of underwater construction. The second method is faster and safer. It's called a sheet pile fence. Imagine that you are building a sandcastle in a puddle. So that the water does not interfere, you put a fence of sticks around it. Only in reality, it's not sticks. These are huge steel piles with locks on the sides. They fit into each other like parts of a Lego constructor. Divers at the bottom guide these piles, and from above, a powerful vibrating hammer hammers them into the ground around the perimeter of the future support. When the steel wall is closed in a ring, the most spectacular thing begins. Powerful pumps begin to pump water out of this fenced space. And a miracle happens. A dry, deep pit appears in the middle of the river. You are standing at the bottom of the river, and there is a wall of water several meters high around you. The only thing that separates from flooding is steel sheets and pump operation. But there is a nuance. If the soil at the bottom is sandy, water can seep from below. That's why they pour a concrete pillow first. It creates an impenetrable floor. And only then the workers go down, install reinforcement, and pour the foundation. When the concrete hardens, the sheet pile fence is cut off underwater, and the finished support remains standing, invisible to those who pass from above. A third method is used in very deep waters, for instance in sea bays where depths reach 30-50 meters or more. Installing sheet piles is pointless here. The water pressure would simply crush them. This is where giant drilling rigs come into play. They are mounted directly onto barges. The barge anchors precisely over the site of the future support pier. A long drill pipe, tipped with a cutting bit, is lowered into the water and bores into the seabed. It drills down tens of meters, through sand and clay, sometimes reaching depths of up to 100 meters. The rotating drill creates a deep borehole. But how do the walls of the hole avoid collapsing underwater? A bentonite slurry, a liquid clay mixture, is used for this purpose. It fills the borehole and supports the walls, preventing them from caving in. Once the borehole is ready, a reinforcement cage, a structure made of thick metal bars, is lowered into it. Then concrete is pumped in under pressure. Here, nature lends a hand. Concrete is heavier than water. It displaces the clay slurry, forcing it upward and fills the borehole from the bottom up. The result is a massive concrete column extending deep into the bedrock. Dozens of these piles are installed around each support pier. Once they harden, they are connected at the top by a concrete slab. This forms the foundation. With the foundation complete, the most visually striking phase begins, choosing the architectural design. The first and oldest type is the beam bridge. It consists simply of a beam spanning the gap between supports, much like a log laid across a stream. It is inexpensive and reliable but unsuitable for long distances. The second type is the arch bridge. In this design, the load is distributed outward toward the banks. These bridges are visually stunning, but they require rocky banks capable of withstanding the outward thrust. The third type is the cable-stayed bridge, a modern classic. It features a massive tower with steel cables, stays, radiating outward to suspend the roadway. Each cable bears a portion of the load. Such bridges can span distances of over a kilometer. Building a bridge involves years of work and hundreds of people. The Crimean Bridge, for instance, rests on nearly 700 piles that extend 100 meters down into the seabed. Yet the fundamental principle remains the same. We do not try to drain the ocean. Instead, we outsmart it. We create small air pockets, steel walls, and concrete pillars. We do not fight the water. We come to an agreement with it. The next time you drive across a bridge, think about what lies beneath. The invisible foundations, the water pressure, and the people who figured out how to build a road where one seemingly shouldn't exist. Thank you for joining us. Subscribe to learn more about how the world works.
Watch this drill bit spin! It goes down, making a hole. Cool, right? Concrete filling from bottom to top. See it rise steadily upwards. That's how it's done. The log bridge is cheap and sturdy, but its span is short. These huge pumps are dewatering the cofferdam. High capacity and continuous operation keep it dry and safe.